spring between those?
No, they are the spring.
Cool.
Okay.
All right.
I'm Kelly.
Introduce yourself.
This is Emily. This is part 2 or 3, I don't know, of explaining quantum computing. It's here. So this is magnetic field viewer. You can kind of see how the field propagates. I don't know. Okay. Anyways, I'll put it back to us. Maybe I should have a little USB. Ooh, I know how we can do it. I can just open the camera here and show it on there. Anyways.
Next one.
So when you have, can you hold this for a bit? So when you have a, so let's pretend this is an electron and it has a up and down spin, or kind of, it has poles because it's rotating in direction.
Right.
So when you're sending electrons, so put it down on the table, when you're sending a stream of electrons, you see how it kind of rotated to fit. So let's do it this way. You see how it kind of rotates? Oh
yeah, it does.
So
it kind of goes.
That's essentially what is happening when someone says the measurement changes the kind of the outcome. Is because when you're sending an electron over here, that electron has a magnetic field.
Right, and it'll pull it out of its regular spin.
Yeah, and what it'll do is, so if it's all in black, that means they're kind of repulsive. But if you put a south-facing
kind of
one,
repulsive.
If you put south-facing, you get this band in between.
Oh yeah. Woo.
And that's the magnetic field lines. So that's essentially, okay. So this is attractive. Let's do it again. And then repulsive is just two black, like they both have black kind of
yeah,
fronts.
I'm like being pushed away here.
Yeah, and we can't make them kind of meet up. Whereas this, we can't help but make them meet up.
They love each other.
These are really shitty magnets. They keep breaking.
Oh, well, that's okay.
So what I just demonstrated, that's the essence of kind of how Schrodinger comes into the equation. So
the cat killer?
Yeah, the cat killer. So he was describing it not in terms of cats, but in terms of atoms and quantum bits.
Mm-hmm. So if any of you haven't heard of the whole Schrodinger's cat thing, it's that there's a cat in a box, and there's nuclear waste or something like that, or a packet in there that it's going to open up, maybe
radiation.
Right, something deadly in there that'll open up and maybe kill the cat, and you don't know whether or not the thing is opened up. So until you open the box, the cat is either dead or alive, but you don't know which it is.
Yeah. So let's translate that phrase into here. So when an atom or an electron is spinning like so, we don't know that it's spinning in this direction until we measure it. Mm-hmm. And there's no way of knowing without measuring. And there's no way of not affecting it when you do measure.
Right.
So basically, what is happening in Schrodinger's cat and how it applies to this is that this gyroscope, let's say, is a magnet here. And in the time of measuring, you send a beam of electrons or photons, and the measurement causes it to flip to either one or the other state. Right. Because it's either repulsed or it's attracted.
Right, just like the magnets I showed you earlier. So I mean, it's always going to affect the thing.
So it's the measurement itself that kills the cat.
Right.
It's the action of taking off the box and measuring it that determines whether or not the cat is dead or alive.
Right. So until the point where you open the box.
Yeah. Until
what
the time
is the
of
assumption
measurement.
with quantum mechanics?
Yeah.
The assumption is.
The assumption is that it's somewhere between 1 and 0. And 1 being up and 0 being down. The action of measuring determines one or the other state.
Right, exactly. And we've already figured out why. Because I mean, that blew my mind. It was like all the simple explanations were like, oh, it's, it just knows.
Yeah.
The act of measuring it makes it so it knows. And it's like, it has a brain and it's like, I can see you measuring me. I'm not going to do what you want me to do anymore. Like, come on.
Okay. The other thing that's the reason why that's kind of complicated and it makes quantum mechanics a little unsettling is that, so let's say you have your electron with spin, let's say it's spinning clockwise here. There's microwave antenna here, and that's kind of what they look like. They look like a squiggly line. And those microwave antennas send signals in either direction, and that kind of changes the spin in this direction. Let's say if you send electromagnetic energy in this way. So it has to send waves in a pulse-like matter.
Okay.
So and the frequency of that is in the gigahertz frequency, like microwaves. And the reason why microwaves heat up food is because they're the right frequency at the right resonance frequency for that, so they're really effective at spinning it up and down and exciting it. Because they send the pulses just at the right frequency to make the spin all the way up. And as don't
they actually send waves at just the right frequency to move the water atoms specifically? Like I thought it was the water specifically.
Yeah, but those are the electrons in the water.
Exactly. Yeah.
So here what they do is they kind of have like a pulse width. They change the pulse width. So let's say you have a wide pulse here. So this is kind of electromagnetic. This is on, this is off, on, off. So by changing the spacing between here, you can be like move this in a short distance, or you can move it in a large distance by having a specifically timed push. Okay. So imagine it being like a swing. So if you have this here, actually this is really good at explaining. If you touch it at the right frequency, you can add up momentum, and that's called the resonance frequency.
Right.
However, when you hit it coming back, you decrease momentum.
Yeah, you get it all kind of confused. Oh, and that is a good way of explaining it.
And what the quantum computer does, it does it on this side and it does it on this side.
Oh, okay.
But it doesn't swing back and forth, it just kind of stays.
It just goes.
Because this is not, we're not measuring the orbit, we're measuring the axis of this and the direction.
Right.
So actually it'd be better to do it. So it pushes it like this needle, and then over like this perhaps. And what you're measuring is the angle of that.
Right. Okay.
So now that we have this angle here, when you're sending the photons to measure it, which affects it will collapse to either this state, the up state, or the down state.
Oh. Which is why they were like, it's either 0 or 1.
Yeah. However, before you measure it, it can be anywhere between the two of those. Oh. But when you do measure it, it's either 0 or 1.
Huh. Yeah, see, the other ones didn't do that.
Yeah.
Yeah, thank you for explaining that.
Yeah. The thing is, the measurement of, is it going to be 0 or 1, depends on which plane you bring this in. Because it flips based off of the perpendicular kind of angle of this.
Right.
So the atom will either flip to this or this. Oh, it doesn't do this versus this direction. So it doesn't flip side this direction. It's like straight up or straight down.
Straight down, yeah, for sure.
And that makes it kind of tricky because you have to now do, what is it again? Sorry. As you're imparting momentum, so let's say this has a spin across here and we're measuring it on these axes. They usually what they do is they do the same calculation, let's say 1,000 times, because every time you get either, so yes, no. So what they do is they do the same calculation over and over, and you get maybe with this measurement here, this specific kind of vector, you would get, let's say, 3/8 would be up.
Okay.
I'll just say this is up and this is down.
No, it's down. Okay.
So you'd get 3 of the measurements would be up, and then maybe, so that's 1, 2, 3. I'm doing it out of 10.
Okay.
And then 8 measurements would be no. And if you do it
you'll have to erase one of those yeses then, because that's not out of 10.
Sorry.
2 yes, And 8 no's.
All is well.
Yeah. Sorry.
So what you're able to do over the long run is the more often you ask it,
Okay.
the more precise your answer can become. Because if you ask it 10 times, you get a decimal point of accuracy of 1.
Right.
If you ask it 100 times, you get another decimal point. If you ask it 1,000 times, you get another decimal point.
Yes, your denominator is larger there.
So you can get a very precise position in here. Depends on how often you measure it, because it always, when you measure it, it collapses to yes or no.
Okay.
And because of
Right, so it'll be like, it's somewhere in here.
Yeah.
Or it's somewhere in here. But are you ever able to figure out if it's actually here? Or you're just able to figure out if it's in this direction?
Sometimes it'll show up as being here because of the way quantum uncertainty works. I don't understand that quite yet.
Okay.
But if you measure it often enough, you should get a quite precise answer on the actual position after you do a set calculation. Does that make sense?
Sort of. Because I don't understand how, like, because you just explained that it either goes up or fully down.
Yeah. No.
So there's how could you figure out? Oh, because it'll be a percentage of whether it goes up or down, and that's how it determines how it's kind of somewhere in the middle. Okay.
The position.
I've got it.
You find out the position of it based on the percentage of yes versus no.
Right. Right.
It's not, you can't measure the precise angle here with one measurement.
Right.
Awesome.
See ya.
Okay. See ya.